Hi, hello everyone. So in this lecture today, I'll be discussing about orthogonality of guided modes. In the previous lecture, I have discussed how the guided modes can be solved for a given waveguide structure, and we have also discussed about the dispersion relation of the guided mode, and also we have discussed about the polarization convention. So there are three different type of modes are there: T-like mode, TM-like mode, and hybrid mode. So all these guided modes for a given waveguide structures, they follow a certain rule, and the major and important rule is they are basically orthogonal. So orthogonality, any eigen solutions, any eigen equation, if you solve, normally whatever the solutions you get, typically they are orthogonal. And in a light electromagnetic wave point of view, propagating in a waveguide, we have to establish some mathematical framework to utilize this orthogonality condition for designing various type of waveguide structures, devices, circuits, etc. So towards that direction, we need to understand first very important aspect of electromagnetic theory is the Lorentz reciprocity theorem. You have to consider any two modes for an electromagnetic wave in a system, and we can show that there are certain relationship they follow, any arbitrary two modes, and that relationship is known as the Lorentz reciprocity theorem. We'll be just discussing that thing, and just a proof the relation, how it is derived. And that Lorentz reciprocity theorem is used to show that the guided modes in a waveguides are orthogonal. So we'll be then discussing the derivation of orthogonality condition. We need some mathematical relation and to prove that, and if it is satisfying that particular relation, then we can say that okay, well, these modes are orthogonal, then they are guided modes. Guided modes are orthogonal. There's eigenvalues, eigenvectors, and then we will just show the normalization of guided modes. So in next lectures, we will be discussing about coupled mode theory. So in the coupled mode theory, we will just try manipulate the guided modes to interact each other, so that they can interact each other, so that we get a particular functionality out of the system. So in that case, we need to know how to normalize individual guided modes in the beginning when you are launching. Okay, so then we know that okay, this is the normalized mode, and then as it propagates, how they are interacting among themselves, you will be able to quantify that. So that is what why we need to do normalization of any guided modes. Of whatever you are getting solution out of the eigenmode solver, that has to be normalized first. Okay, so let us move on. So again, I take reference of this type of waveguide structure. It is just x direction and y direction, and z is the x, y, z. That means out of the screen, that means propagation direction. So mode will be confined in the xy plane and two-dimensional waveguide mode, and then it will be propagating along z direction. And then let us consider any two arbitrary guided modes. Let us consider it is say, for example, any multimode waveguide structure. W is considered such that it is a multimode structure, or any other type of waveguides also you can consider, where you can have a number of modes can be supported. It can support a number of modes, meaning it has a solution, number of guided mode solutions it can happen. So as I mentioned earlier, that whenever you are solving full vectorial all the wave vectors and all the eigenmode, eigenvalues you solve, some of the modes you will be seeing as a guided mode, and some of them will be leaky and radiating modes. Okay, many of them you will be getting. Only we are interested, we will be focusing only on the solution which are actually guided mode, because that is what we need for our integrated optics, for photonic integrated circuits. And here also we will be just restricting ourselves any two arbitrary guided modes, not all other mode solutions. So first guided mode we designate as mode 1, we just give a index like 1, where associated electric field vector is E1 and magnetic field vector is H1, and you can have this vector field, entire vector of the field that can be xy dependent mode and traveling wave factor, that means omega t minus beta 1z. Both this one will be multiplied to magnetic field and electric field. Okay. Similarly, mode 2 you consider another mode where the electric field and associated magnetic field is designated at E to H2, and xy distribution for magnetic field and this one. And then this Lorentz reciprocity theorem says that any two solutions, eigenmode solutions, okay, and in this case we will be only focusing on guided mode, but Lorentz reciprocity theorem for all types of modes, but here we will be trying to take it as a restricted eigenmodes, guided mode I meant to say. So that is say the divergence of E1 H2 E2 H1, and if you subtract them and take a divergence, then it will be 0. That is actually Lorentz reciprocity theorem. You know that E cross H, that is the value is known as Poynting vector, right? Poynting vector, it is called Poynting vector. That means energy flows along in the perpendicular to, both perpendicular to the E and H. But whenever electromagnetic wave propagates as a guided mode, for example, as a different modes propagates, so then I can say that what is the total field is total energy is flowing. I can get total field of electric field coming out of all the modes, total field coming out of all the magnetic fields. Then I can say that E cross H, what is happening, that is the total energy. But if I restrict ourselves, what is the energy carried or power carried by individual modes, then we must write EM cross HM star half real part, and this is the per unit area you have to integrate. That is the energy flow, energy carried or power carried by a mth mode. But in this case we are involving two modes, not one mode, two modes. If two mode is there, then if I try to get E1 cross H2, not E1 cross H1, I am not considering E1 cross H1, that is the power carried by the one mode. But we are considering E1 and H2 and vice versa, E2 and H1. And then if I try to take, they will have some value. But if you subtract them and they are taking divergence, total value, that will be 0. I want to prove that first, because that will be helpful for our setting up orthogonality condition for the guided modes. Okay, proof. Let us take a curl equation. So curl of E1 equal to minus del B del T, right? J omega mu 0 H1. Okay, minus del B del T, instead of that I am writing here. And curl of same mode E1 and curl of H1 I am writing. E1 I am just entering here, H1 I am entering here. Okay, H1 is what? That means curl H equal to del D del T. It is dielectric medium, so sigma equal to 0. So J omega epsilon E1. So it is a mode 1. Mode 1 curl equation I am just writing for curl E and curl magnetic field. That is for mode 1. Similarly for mode 2, curl of H2, J omega curl of H equal to J omega corresponding E2. Curl of E2 minus J omega mu 0. So all this curl equation. I clapped this because here you see E1 cross H2. That's why I have just written E1 and H2 curl equation I have just written side by side. Okay. Starting from here, next, what you do? This equation you just take H2 as a dot product both side. H2 dot product both side. So H2, this one, you are getting this one, and here H1 was there, H2. Same thing I am repeating, just H2 dot product I am taking. And from this equation, what you are getting? You are just taking E1 dot. You are taking E1 dot here, because H2 involved, E2 involved. So we are just bringing E1 here. Okay, E1, this one, and then E2. So two equations I just got here. Okay, let us see what is happening. You subtract them. Just subtract this thing. H2 curl of E1, this comes here, and this comes here, subtracting, and left hand side comes here, right hand side comes here, okay, minus this minus a. So if I take minus j omega, it is coming like this. So I'm subtracting this 2, whatever starting from the curl equation, this is straightforward. Then what do we do? You use this vector identity. You see, if you take a cross of any two vector a and b and take divergence, they can be just written as like this. So it is like a dot b cross c, a dot b cross c. This is a vector, this is a vector. So vector identity you can write. That's actually we borrowed from the vector algebra. So we can write like this, right? So it is something right hand side, if you see, it is like this left hand side of this one. This vector identity right hand side, it is looking like that. What is that? That A is E1 and B is H2. So if you are writing A is E1 and B equal to H2, so then divergence of A cross B equal to this one. So divergence of, that means we can write this thing together, left hand side as a divergence of E1 H2. E1 A cross B. Divergence of AB, A equivalent to E1, B equivalent to H2. So from the vector identity, we are just after subtracting, left hand side can be compacted as like this form. And what about right hand side? As it is I have written. So I get one equation here. This is one equation. Same way, if I start from here, same procedure. Okay, for example, here we have just took a dot product of H2. Here I will be taking a dot product of, say, H1. And here I will be taking a dot product of E2. Then follow the same process, same way, then you get another equation. Another equation, there, if you just compare, they are identical. Basically, E1 is converted into E2, H2 is converted into H1. Otherwise, same, you are trying. So, but they are different, basically. So, in this two equation, if you see, first term E1, H2 of the Lorentz, that expression we have achieved. And second one E2, H2, that means we have to subtract these two. If you subtract, right hand side is identical if you see. So if you subtract, then it is 0, proved. So that is what we have written. If you just subtract them, then divergence of E1, H2, E2 cross H1 equal to 0. This is actually called Lorentz reciprocity theorem. We will be using that next. Okay. We have written Lorentz reciprocity theorem. We have considered two modes. Mode 1, mode 2, and start from Lorentz reciprocity theorem. You know this one is nabla is a vector we represent like this. Okay, so I just decompose, this is xy, because our waveguide cross section is xy cross section. I just combine them together as a one vector called delta t, transverse nabla. So this is a three-dimensional nabla where you are having x, y, z, all the components are there. But if I just put transverse means transverse, that's cross section, transverse section of the waveguide. Okay, that is delta t. So I can write delta t plus az del z. So that is what this nabla is decomposed into this one and dot product, and then this E1 H2, that means this E1, whatever value E1 multiplied by this one, right? E1 xy multiplied by this one, and then H2 multiplied by this one. So we are just putting E1 xy, H2 xy, and then this one. So E1, if I write E1, that means this is capital E. This is means non-italic. And when I am writing here E1 xy e to the power j omega t minus beta 1 z, and H2 means I will be writing H2 xy e to the power j omega t minus beta 2 z. So E1 H2 means E1 xy H2 xy, E1 xy, H2 xy, and this one if you multiply, e to the j 2 omega t beta 1 plus beta 2 z. So that is the thing. So that means this one multiplied by this one, that is taken factor. Similarly E2 H1, E2 xy, H1 xy, and then if you multiply U2 and H1, the phase factor will be same. That is common to both the term. I have written this one. So that this way I am writing so that I can take this as a factor, this can be removed. Okay, so this is actually equal to 0. What we do then, I just do this nabla t transverse dot, I have taken this one, this I have taken xy, and then this one if you just do operate here, all these are x. Okay, this should be del z, not t, del z. Okay, this should be del z, and then del z if you operate, then what you will be getting? You see beta 1 plus beta 2 z will be factor. So minus j beta 1 plus beta 2 you will be getting, right? So this will be here minus, and you are taking that to right hand side. Okay, so this may be minus plus, so that will be equal to 0. So this side, this will be again minus sign will be there. Okay, so that means what I am writing, I am just operating on this one. First term I keep as it is, because it is a transverse del xy. I don't know the, whatever the value is there, that derivative will be there. I just kept as it is. And this one if you operate on that, that means you have to operate on that. This is the z dependent function is there. So minus j beta will be there, right? Minus j beta, if you just operate on this one, you will be getting beta 1 plus beta z in both cases, here and here, right? So that is the value we will be getting this side. Okay, so I think this is a correct sign, no minus sign will be there. Yeah, because here you will be there and here will be there, so that will be taken to that side. Cool. So one term this one, another term you will be getting this one. This term will contribute here as well as here. So you can write like this. So this term will be constant, this side will be there, along with that this z dependent function will be there. Just simple derivative you just do. It's not a rocket science anything. Okay. So now next step, important step. You have to integrate both sides over xy plane. Xy plane is the waveguide plane, right? Cross sectional plane. If I just integrate both sides over xy, so this is almost divergence, transverse, two-dimensional divergence I would say of this one, and you are just integrating over dx dy. And right hand side, j beta 1 plus beta 2, and then az is there. This az thing is there, dot product. You are just putting dot product here. Okay, so you are writing minus j beta by zt, and that side to be going. This is the thing is there. Okay, so right hand side again integrating minus infinity to plus infinity, will be getting like this. So left hand side, right hand side. Now let us focus on left hand side. Okay, here I have just highlighted here left hand side and right hand side again, just to proceed. Okay, delta t, nabla t, and here right hand side this one. Started from Lorentz reciprocity theorem again. Now applying 2D Gauss theorem to left hand side. This one. What is Gauss theorem? Gauss theorem says that if you are taking a volume integral, divergence of any vector, right, that will be actually equal to a ds surface integral. So if you are taking a divergence of a vector and then volume integral, that will exactly equal to surface integral of that volume. In the volume surface, whatever the value is there, you take a dot product with the surface element and then integrate over. That will equate to the divergence of the that vector. That is actually called Gauss theorem of divergence. Gauss theorem for 3D. Gauss theorem for 3D. But we want to apply this Gauss theorem in 2D case. Here also divergence, but 2D. Only xy plane. Your z plane you are forgetting. So when you are considering 3-dimensional volume and applying Gauss theorem, you are reducing it to surface. But when a 2-dimensional problem, divergence theorem, if you are reducing, then it will be reduced to the perimeter, line. So 3-dimensional reduced to a plane, and you are getting a surface integral. 2-dimensional divergence, if you use Gauss theorem, you will be reduced to a line, perimeter only. One line you will be getting. So that's why the left hand side, if you just apply divergence theorem, the entire vector I am writing dot dl in the perimeter. So if you have a surface, waveguide surface, you are taking divergence and then integration over the surface. Instead of that, ultimately if you do the line integral of that surface, whatever the cross section you are considering, only the perimeter region, if your value you are just taking and then integrating, that will be the same. That is the divergence. It is a vector. This is a vector. This is a vector. Same way divergence theorem I am using. But problem is that once you do that, and I have mentioned that you, while starting from the power calculation, everything in the previous lecture we have said that you can do E cross H minus infinity to plus infinity. X can be minus infinity to plus infinity. Y can be also minus infinity to plus infinity. Okay, so this can be done. So here also, when your cross section you are taking a large area, but your waveguide core is a very small area. Large area cross section if you are integrating, and then you are reducing to the line integral, and guided mode when x tends to infinity plus minus, y tends to plus minus infinity, that particular region when it is extended to infinity, the field E1, H2, all the, if they are from guided modes, they should be 0, because guided mode is confined within the core. So outside it will be 0, outside the core, far away from the core, x equal to plus minus infinity, that will be 0. So that means this left hand side, if you apply Gauss theorem, you are applying Gauss theorem means that is actually directly, you can just use. You don't need to use Gauss theorem left hand side, similarly Gauss theorem right hand side, because left hand side Gauss theorem actually helps to simplify. Right hand side as it is I am keeping. So left hand side, if I just extend minus infinity to infinity, obviously this is 0, no doubt about it. It is for any cross-sectional, for large cross-section if you are doing, that is 2. But if you are just concentrating your cross-section lower than the waveguide mode size, that is not correct. So we are applying your integration should extend large cross-sectional area. Okay, so now let's move on. So we can write, we obtain for the forward propagating modes like this. Only this one I am writing. We are considering 2 modes, they are forward propagating, because minus minus we are considering, right? For forward propagating, minus omega t minus beta z, that is meant for forward propagating wave. So left hand side, right and left hand side is 0 means right hand side equal to also 0, must be equal to 0. We have written that. Okay, so that's good. Now I just consider for co-propagating modes, whatever we have derived, this one, starting from the Lorentz reciprocity theorem. Now you see this mode 1 propagating in the forward direction, mode 2 propagating in the forward direction. Now if you just consider this, both the modes, they are free to, because if a mode is allowed to propagate in the plus z direction, it can also identically propagate in the minus z direction as well. Mode 2 also case will be same. Now we have tried to see the 2 modes, identical mode distribution, you are allowed, they are sending energy in the forward direction. Now one of them, if it is in negative direction, then also we can try to use, that is also a mode solution, that also obey Lorentz reciprocity theorem. So one of them is the positive direction, another is a negative direction, counter propagating. So in that case, if you treat same way, then what you supposed to get? You get this thing. So one is beta 1 z minus beta 1 forward propagating, another is negative direction, but the same mode. Same mode. Mode field distributions are same. H2 I am considering also same. Only their direction changed. Field distributions, everything is same. Direction change. So normally, you know, one electric field, if we are propagating in this direction, if it is E field here, this direction, then H field will be out of the screen. That will be propagation direction, right? This is H. Now, if propagation, if you are changing, then this E field sign will be changed. So not only the sign in the phase factor will be changing, also the transverse direction, this magnetic field or electric field, one of them will be, direction will be changed, minus sign will be using. So in the use of your Lorentz reciprocity theorem, that particular fact you have to keep in mind. If you do that, then you are getting similar equation, almost like co-propagating mode, same, but except minus sign you are getting plus here. That's the difference. So for 2 modes propagating in the opposite direction, you can use reciprocity theorem. You are getting the same divergence Gauss theorem, Gauss divergence theorem you can use, and then integrate over entire cross section, and then you are getting this thing. Now you compare these two. They are same mode, just direction is different. Mode means normally you consider beta 1, beta 2, that is the solutions at actual pattern I am just considering, right? So that pattern, field distribution, xy distribution, and this whatever field distribution here, whatever field distribution here, they are same. Whatever field distribution here, whatever field distribution here same. So in these two equations, no, you don't have any use of beta, plus or minus, nothing is there. That is factored already. Rather, you have the mode shape xy, cross-sectional distribution is there. If you compare them, it looks like that it is like a minus b equal to 0 and a plus b also equal to 0. A minus b equal to 0 and a plus b equal to also 0. What does it mean? It means it's a equal to b. Right? So that thing, this should be equal then. So if that is the case, then what I can write? This one should be equal to this one. I have written that one. So if I write that equal to this one, then for any two modes, sorry, not that equal to, actually, if you have a minus b equal to 0 and a plus b equal to 0, that means each of them equal to 0. A also will be equal to 0, b equal to 0. Otherwise, a minus b equal to 0, a plus b equal to 0 will not be there. Okay, so in that case, what I can write? This one equal to 0 or this one equal to 0. I just take first term. The first term, if I take instead of 1 and 2, now I just, for generalizing this thing, I can consider mth mode. One should not misunderstood with the 1 means it is first mode and 2 means second mode. It can be any mode. If you have a 10 different modes, you can choose m one of them. N, if it is different modes, you can choose n is one of them. Obviously, while deriving this thing, we have considered m not equal to n. Because if they are same mode, then E1 and cross H1, it should be H1, right? That means power carried by the same mode. So whatever I have solved here, that is, you have to consider that both the modes are separate modes. Okay, separate mode, they can be forward direction, also backward direction. One of them you can choose. You are just clubbing one mode and another mode forward direction, and or that same mode reverse direction. These two situations you have considered, but they are actually different mode. M not equal to n. That is what you have considered, and you end up with this one, and that is actually called orthogonality condition. If two modes you are just considering, and mth mode you are taking electric field, and nth mode you are taking magnetic field. If you are taking a cross product, just cross product alone, it cannot be 0, but if you integrate over the cross section, then only it will be 0. So E cross H, if I take E field from one mode and H field from another mode in a particular point and take E cross H, I may get a value. But the situation here is saying that if you are taking E field and H field at a particular point and you integrate that value E cross H, E1 cross H2 over the cross section, then only you will be getting 0. One particular point it may get value, but integration, that will be 0. That is actually orthogonality condition. So that can be a little bit proceed forward. So we have written, this is the so-called orthogonality condition. We are just trying to see that, okay, this orthogonality condition, how we are using for our other application like normalization of a guided modes. Yeah. Let us see. Okay, so now you see, I know that power carried by mth mode is just power half real part em cross hm. M same. That means this n become now m, same mode and az direction. This is again and again we have discussed. That's the total power carried by a mode can be expressed like that. Now move on. If power carried by the individual mode is normalized to 1 watt, okay, then the orthogonality condition can be written as this one. You will be writing like this: half em hn equal to delta mn watt. If you see, if this is equal to 1 watt, we know that power carried by a mth mode. Now here m and nth mode, both the modes you are considering. When you are putting m equal to n, that means that is becoming this equation. So m equal to n, that means delta mn, this will be 1 watt. M not equal to n, that will be 0. So this thing, in general, just considering the power carried by a mode and the whatever the Lorentz reciprocity theorem we have used, you club them together, you can write orthogonality condition in this form. Okay, now you see, let us consider T-like mode. I have discussed earlier that a guided mode can be T-like, can be TM-like, can be hybrid also. If I just consider T-like mode, that means your electric field will be in the XZ plane and magnetic field in the YZ plane, Y component, Z component. And obviously, I can always consider that EX probably, EX component, Z component there, EX normally is higher. So that transverse electric field is there considering propagation direction, and here HY can be larger. That type of specialization you can consider, you may not consider also, that's fine. Power flow per unit area along a propagation direction, we can represent like this. This thing actually we are writing again, E cross A star, just any given mode we are considering. And considering these components associated with a mode, you just take E cross H, considering these are the components. Okay, E cross H, that means you can consider like this, a X, a Y, unit vector AZ, and then you have EX, 0, EZ, and here you will have 0, HY star, HZ star. Now power flow along Z direction, if I just consider, that means I have to consider Z component of the E cross H. That means EX multiplied by HY. So this one multiplied by the EX HY, right? Like that. I think this should be plus sign probably. Yes, EX 0 Y and HY star HY. So this would be plus sign there. So power flow per unit area along the propagation direction, this is a plus sign. Okay, this component, EX HY component, if it is known, then we can write like that. Okay, fine. Now, if I just write this one, okay, this one little bit modification I want to do. How we are doing? Because instead of electric field, magnetic field component, we know that once we have electric field component for a given mode, I can find out what is the magnetic field component from this Carl equation we have shown earlier already. Using this Carl equation and these field components, I can find out what is the value of HY, like this. Okay, so if this HY I am getting, I think this minus sign will be cancelled somewhere. So then whatever you will be getting, this here if you are putting, you can write this equation, you can modify here if you are just writing this one. Then what you are getting? Beta by 2 omega mu, right? Beta by 2 omega mu times EX times EX star. This HY star means, HY star if you write, it will be EX star. EX by EX star, right? That will be 2 omega. It will come like this, power flow will be 2 omega mu by beta times EX XY and EY XY dx dy. That will be power flow 2 omega. That's if that is actually 1 watt, like this, whatever you consider. So this equation we can now modify in terms of only electric field associated to the nth mode also. So electric field with the mth mode, and this comes electric field with the nth mode of the this magnetic field converted into nth mode. Then this will be multiplied by 2 omega mu by beta this side. That should be equal to 1. If I just simply write this thing should go that side, right? So that, sorry, this would be beta by, this should be beta by 2 omega mu. Beta by 2 omega mu, that's why it is coming this side, 2 omega mu by this one. So instead of beta, since we are involving m and n, that's why we are writing here, just simply because m equal to n means it is beta m basically, it will come. Otherwise it will be 0, delta m n equal to 0. That's why in general we write beta m times beta n square root. So if they are there, ultimately 2 omega by beta it will be there, because here if you just put this one you are putting, then it will be beta by 2 omega mu. This power will be coming. So just use your Poynting theorem, what is the power carried by a mode, and starting from Lorentz reciprocity theorem, where you are getting m not equal to n, club them together, then you get a very nice equation involving only electric field. So you don't need to bother about magnetic field. So this thing actually we can use wherever necessary for orthogonality condition. We can check that if electric field coming from mth mode and electric field coming from nth mode, if you are taking their, if they are vector, you can take a dot product and integration over dx dy, and if they are identical mode, then you will get 2 omega mu by beta times 1 watt, because 1 watt is always there, otherwise that will be 0. So electric field of two different modes if you are having, then just integrate over them, then they will be 0. We just take an example. Suppose you have a 1D waveguide. If you see fundamental mode will be like this. So this is your say EY 0 X. This is X axis, this is Z axis, this is your X axis. And then higher order mode, if you see, then it will be like this, right? So this is, for example, electric field positive direction oscillating, and one half higher order mode EY 1X higher order mode, one half positive, another half negative. So if you just try to see this equation, that means you have to see EY0X and EY1X dx. What would be the value? Because you know, if you just every point you have to find out what is the value of EY0X and what is the value of EY1X. So if you just see upper half, if you just multiply them and integrate, you get a positive value. And lower half, you just multiply them and you get integrate them, you are getting a negative value, identical amount. So if you integrate them, you're supposed to be 0. That means any two mode, it can be 10 modes, out of 10 modes, any two modes you consider, see their electric field distribution, there should be identical polarization, identical type of situation you consider. If not, you have to take a dot product, of course. So any two modes, their electric field distribution if you take, and if you integrate over the cross section, they must be equal to 0. And if they are coming from same mode, if you integrate, they will be normalized to 2 omega mu by beta, propagation constant. So this fact I will be using to describe coupled mode theorem, which is the basic building block for the integrated optics or integrated or photonic integrated circuits. That will be the subject of our new lecture, next lecture. Thank you very much.